So what I'm planning on doing in this video is deriving the equation for the conservation of mass. And it might seem odd that we're going to be looking at the conservation of mass in thermodynamics, but basically we need this if we're considering an open system. And so basically an open system means that we have fluid or mass flowing into or out of our system. And so the reason why we might need to use the conservation of mass is we might need to calculate something like the geometry of a part of our system, or some other info that we may need in order to solve the first law, which is the energy balance for our open system. So there are a few different ways to derive this. So I'm going to show you one way, but don't panic if you see it done other ways. What you want to do is just go through and write down the derivation and just make sure that you're understanding each step of it. So basically what we want to start with, let's say this is our control volume. And remember, a control volume is just, it's the terminology used for the area of interest, or basically the volume of interest that we're interested in an open system. So an open system means that we have mass flowing in and out. So this is our control volume. This is called the control surface. So the volume is CV, control volume. The surface is control surface, or CS. And then we have some fluid that's flowing in. So I'm just going to call this mass in, and fluid that's flowing out. So I'm going to call this mass out. And so, like any conservation equation, we can start out by just writing something really simple. So we can just say that the mass in minus the mass out is equal to the change of the mass in the control volume. And then we can consider this on a per time basis. So how is the mass in the control volume changing with time? Well, for that we would use the rates. So the mass flow rate in with time minus the rate out with time is equal to, this is dm cv dt. And this dot just means that this is a rate. So this means that this m dot is equal to dm dt. So this is basically saying that this is the mass flow rate and it's the amount of mass flowing through the cross-sectional area with time. So that's all we're saying with that. So we're saying that the amount of mass flowing in with time minus the amount of mass flowing out with time is equal to the change of mass in the control volume with time. And that makes sense because if we have more mass flowing in than what's flowing out, the mass in the control volume is going to be increasing with time. Or the opposite, if we have more mass flowing out than what's flowing in, the mass in the control volume is going to decrease with time. So what I'm going to do is rearrange this equation slightly. So dmcv dt, and I'm just going to add the mass out. I'm going to put everything on the same side. So I have dm cv dt plus m dot out minus m dot in is equal to 0. So basically I've just put everything on the same side and set the equation equal to 0. Now what we want to do is we want to figure out how we're going to calculate these things. So we have the change in the change of the mass in the control volume with time, and we also have this mass that's flowing in and out of the control volume. So the first thing I want to do is I want to consider this part of the equation, and I want to come up with a way that we can calculate the mass that's flowing into or out of the control volume, and then we're going to look at this other term second. So we're looking at this one first. So let's just look at a surface of our control volume. So let's say that this is just the surface of the control volume, and this is a differential area on the surface, so dA. This is our control surface, and then our control volume. And let's say that we have some fluid that's flowing through this surface. So this is fluid is flowing through the surface with some velocity. And the velocity is a vector because it has both magnitude and direction. So what we can do, well, what we're interested in is the normal component of the velocity. So the normal component of the velocity, first of all, we need the unit normal vector. So the normal component of the velocity is just the dot product of the velocity with the unit normal vector. So the normal component of the velocity is equal to the dot product of the velocity vector with the unit normal vector, and this is equal to the magnitude of the velocity multiplied by the cosine of theta. And this is theta right here. So the reason why this is the case, let me just remind you real quick what the dot product is. So the dot product is just going to be the magnitude of V multiplied by the magnitude of N multiplied by the cosine of theta. Well, since this is the unit normal vector, N is just equal to 1. And it's because this is the unit normal vector. So now what we can do is let's consider a differential amount of mass. So I'm just going to call this dm. And this is going to be equal to rho. So basically this is saying that we have a unit amount of mass, and this is equal to rho dV, and the reason why is because the density is equal to the mass over the volume. So mass is equal to the density multiplied by the volume. So then what we can do is let's consider this volume. So the volume is equal to the area multiplied by dx. And this is actually dA dx. So basically we have dm is equal to rho dA dx. Now what we can do is we can write this per unit time. So per unit time we have dm dt, which remember this is just equal to m dot, is equal to rho dA, and I'm just going to leave that like that, dx dt. So this dx dt should look familiar. The dx dt is just the velocity. So remember from physics, dx dt is velocity. So then we have that this is equal to rho v dA. And I'm going to write a cursive v just to specify that that's the velocity and not the volume. So now what we have is, well, so we know that, like, if we go back to this velocity here, the velocity that we want to consider is the normal component of the velocity. So this is equal to rho v dA. And the normal component of the velocity is rho, and then we can put in the dot product, so V dot N dA. So now what we want to do is we have this fluid flowing into or out of the control volume. Like let's say we have fluid here and fluid here and fluid here, fluid here. What we want to do is we want to add up all of the fluid that's flowing into or out of the control volume. So what we can do is we can sum all of the mass flow rate in or out of the control volume over the entire surface. So to do that, we get that M, and this is dm here. We get that M, so the mass is equal to, and let's sum this over the control surface. So this is equal to dm, which is equal to, and let's, over the control surface, so this is rho, the dot product between the velocity and the normal vector, dA. So what this is doing is this is summing the mass over the entire surface. So we're summing over the entire surface of this control surface, and we're adding up all of the mass that's flowing into or out of the control volume. And one really nice thing about this equation is this equation accounts for the direction of the flow automatically. So this accounts for direction of flow automatically. And how that happens is with this dot product. So if we have, so remember the dot product, so this the V dot N is equal to V cosine theta. So if theta is 0, the cosine is just 1, so that means that V dot N is equal to just the velocity. And so this basically represents the max flow possible. And this makes sense because if we look at our control surface again, so let's say this is our dA. If the velocity is, if the cosine of theta, or sorry, if theta is equal to 0, that means the velocity is normal to the control surface. So then we have V here and then N. So this is going to give us the maximum amount of flow, and this makes sense because the flow is basically flowing normal to the surface. If, let's say that the flow is 90 degrees to the surface, so let's say this is our flow, then our angle here is going to be 90 degrees, and so then we have V dot N is equal to V cosine of 90, which is 0 because the cosine of 90 is 0. So this basically represents minimum flow. And this makes sense because if the flow is basically parallel to this control surface, that means that there's no mass going into or out of the control volume, it's just flowing parallel to the surface. And then if we have, like, let's say that the angle is 180 degrees, so then we have theta is 180, then we have V dot N is equal to V cosine 180. The cosine of 180 is negative 1, so this is going to be equal to negative V, so the velocity. And so this is basically saying that there's flow into the control volume, or basically it's in the opposite direction of whatever it is we're considering. And so basically if Vn, and remember Vn is equal to V cosine of theta, if this is going to be positive if theta is less than 90 degrees, and it's going to be negative if theta is greater than 90 degrees. So basically, if we consider this equation where we're summing over the entire surface and we're adding up all of the mass flowing into or out of the surface, this dot product between the velocity and the unit normal vector takes into account the direction of the flow. So it's going to already take into account whether the flow is into or out of the control volume. Okay, so this basically represents, like if we go back up to the mass balance that we originally wrote, so I'm looking at this equation, and I'm just going to rewrite this down here. So we had dm cv dt plus m out minus m in is equal to 0. So this right here that we just derived takes into account this part of the equation. So this is taking into account the mass flow into or out of the control volume. Now we want to consider this term. So this is basically saying that, so if we have mass flow into or out of the control volume, then if the mass, say that there's more mass flowing into the control volume than what's flowing out, then the mass in the control volume is going to be changing with time. Let's go back to this. So we've already seen this equation. So the differential amount of mass in the control volume is equal to rho dV. And so we've already seen this. So remember, this is because the density is equal to mass over volume. And so what we can do is we can sum up all of the mass in the control volume by integrating over the control volume. So basically the mass in the control volume is equal to, and we're going to integrate over the control volume, so rho dV. So now we have all of the mass in the control volume, but now we want to consider how is the mass in the control volume changing with time. Like that's what we're interested in, this mass balance. So what we can do is we can take we can say dm cv dt is equal to d dt, and then this is over the control volume, and then rho dV. So now what we can do is we can piece this equation together. So I want to take this equation and I just want to put the pieces together that we've derived. So I'm going to rewrite that equation, so just so it's all on one page. So dm cv dt plus m dot out minus m dot in is equal to 0. So we've said that this is equal to that, and then the m dot out minus m dot in is equal to this. So let's just write those into our equation and kind of piece it together. So we have d dt, control volume, rho dV, and then this is going to be plus, and this one is over the control surface, rho v dot n dA is equal to 0. So this equation is the general conservation of mass. And what these different terms represent is basically just how we derive them. So this first term is the change of mass in the control volume with time. So change of mass in CV with time. And the second term is the net mass flow into or out of the control volume. So net mass flow in or out of, well, this is actually, so into or out of the control volume. So this is the net mass flow basically across the control surface. so in or out of control volume, or across the control surface. So now what we can do with this equation is we can split this second part. We can split this part of this equation into two parts. So we already know that this represents the mass flow out, or the mass flow in minus mass flow out, or the way it's written here, where I have everything on one side of the equation, m out minus m in. But we know if we integrate across the control surface, we're going to get all of the mass flow in or out. So what we can do is we can rewrite this equation. So we have d dt cv rho dv, and then I'm going to take the second part of the equation and split it into two parts. So I'm going to have the sum of all of the mass flow out of the control volume. So this is out, and this is going to be rho, and then this is the normal component of the velocity. I could write the v dot n, but I'm just going to write the normal component of the velocity multiplied by the area, and then minus, and then we want to sum up all of the mass flow out. So this is rho multiplied by the normal component of the velocity multiplied by area, and this is equal to 0. So basically these two summations are doing what this integration is doing. This integration is summing up all of the mass flow in or out across the control surface, and these summations are adding up all of the mass flow out minus all of the mass flow in. And this can be rewritten as d dt, and then this is rho dv, and this is equal to the mass flow rate in minus, and this is summing up all of the mass in or out, so this is out, and this is m dot. So one thing we want to consider with this equation is the orientation of our control volume, because notice how, so this velocity is the normal component of the velocity. And remember, so if we orient our control volume, let's just say that we have fluid flowing through a pipe. So if we orient our control volume so that it's perpendicular to the direction of flow, our control surface. So let's say this is our surface, and if the fluid's flowing through the surface so that it's basically normal to our control surface, then remember this, so that our normal component vector is right here, so then our dot product, so v dot n, is just equal to the velocity. So this is going to greatly simplify the mathematical analysis. So basically what that means is that if we have this rho, so v dot n dA, this is just going to be equal to rho v a. On the other hand, if we decided to maybe orient our control surface in a direction that's not normal to the flow, like let's say our flow is still through the pipe, and let's say that for some reason we decide to select our control surface like this, then the velocity is, then we're going to need to consider the dot product, because our normal vector is here, so this is the normal vector, this is a velocity vector, and then this is our angle theta, and so then rho v n dA does not equal rho va. In this case, it's going to be rho v cosine whatever that angle is, A. So basically, if you can orient your control volume in such a way that the surface is normal to the flow, then you're going to greatly simplify your analysis. And most of the problems in this class, it's going to be pretty straightforward how to orient your control volume, because usually we're going to be looking at flow through a pipe, and so it's pretty easy to orient your flow so that your control volume so that the flow is normal to the surface of the control volume. So let's go back to, I'm going to go back to this equation, so the general conservation of mass, and I'm going to show you one thing with that, and then I'm going to show you some simplifications that we can make to this equation so that we can actually use it to solve problems. So I want to go down here and rewrite that equation. So basically we have that d dt is control volume, rho dv, plus, so remember this first term represents the mass and how the mass changes in the control volume with time, and then the second term sums all of the mass flow in or out of the control volume. So this is v dot n dA is equal to 0. So what we can do is we can use Gauss's theorem. So just write that down. So Gauss's theorem. And Gauss's theorem says that the integration over a surface, so rho v dot n ds is equal to v, and then the divergence of rho v dv. So what we can do is we can replace this term with this, because this term is basically this, so we can replace it with this. And if we do that, we get that d dt, cv rho dv, plus, and then this is basically the volume, and then the divergence, so rho v dv, and this is still equal to 0. I forgot to, whoops, on Gauss's theorem. So up here, this is still equal to 0. So now what we can do is we can say, okay, well, we can rewrite this like this. So v, and then the partial of rho dt plus the divergence of rho v, and then this is dv is equal to 0. So then this is equal to d rho, or the partial of the density with time, plus the divergence rho v is equal to 0. So this is the familiar form of the continuity equation. So this is what you'll often see for the continuity equation. So basically what this says is this basically represents what we already had. So this is this was the equation that we originally derived. So this just says that the change in the mass and the control volume with time plus the, well, is basically equal to the mass flow in or out of the control volume. So what this is basically saying is that the change of the mass with time, and then this term, the divergence, physically represents the rate in which density exits or enters a given region of space. So this equation is basically saying the same thing. All right, so now what I want to do is I want to go back to go back to this equation, and I want to look at a few simplifications that we can make depending on if we have steady flow or incompressible flow. So what I'm going to do is go down here and rewrite this equation. So d dt rho dv plus, and then we had, and I'm just going to write this for now as we had out, so m dot minus in, and then this is m dot is equal to 0. So let's assume that we have steady flow. So what steady flow means is that there's no accumulation of mass in your control volume. So basically, steady flow means no accumulation of mass in your control volume. And so basically what that means is that your mass isn't changing with time in the control volume. At every point in time, the mass that you have in the control volume is the same. So that means that this term is equal to 0. So what that means is that your mass flow out is equal to the mass flow in. So this is in and m dot. So then what we can do is we can say, okay, well, since the mass flow in is equal to the mass flow out, this is the case of steady flow, so this is the case of steady flow. Let's say that we have a single stream, because this equation is summing all of the streams that we have into or out of the control volume. So if we have a single stream, we can call this, and this is steady flow, so we can consider a single stream steady flow. If we have a single stream steady flow, that means that we only have one stream in and one stream out. So this would be like a pipe. So we have mass in, mass out. So this is just equal to m out is equal to m in. So this is often abbreviated as SSSF for single stream steady flow. And then one more assumption that we can make is, let's assume that it's incompressible. So if we have an incompressible fluid, that means the density is going to be constant. So an incompressible fluid means that rho 1 is equal to rho 2. And so remember, if we go back and rewrite this, so m dot is equal to rho multiplied by the velocity multiplied by the area. So that means that m dot in minus m dot out is equal to, I'm going to change this out and in to 1 and 2. So down here, I'm going to have m2 is equal to m1. So then this is rho 2 v2 a2 is equal to rho 1 v1 a1. If rho 2 is equal to rho 1, these just divide out, and we end up with v2 a2 is equal to the velocity of 1 multiplied by the area of 1. And so this is for the case of incompressible flow. And we can also write the summation. So this could be, well, actually, let's write so the velocity multiplied by the area is the volume. So I'm going to put velocity multiplied by the area is just the volume. And, well, volume per time. So the velocity multiplied by the area, you end up with volume per time. So this is basically a volumetric flow rate. So then this is just equal to the volumetric flow rate in is equal to the volumetric flow rate out. And we can also have multiple inlets or outlets. So let's call this, I shouldn't have changed this to 1 and 2. Let's just say this is out and this is in. So this is out, so V dot is equal to in V dot. So these are both for the case of incompressible flow. And this can be a little bit deceiving because remember there's no volume balance, like there's no conservation of volume. So there's conservation of mass, conservation of momentum, conservation of energy. There's no conservation of volume. So this is not a volume balance. I just want to be clear about that. The only reason this is true is because we're assuming incompressible flow. And this is a good assumption for a lot of liquids. So you'll see that you can make this assumption a lot of the time, but just be aware that this is an assumption that you're making. Alright, so what I want to do is we've derived a lot of equations, so I just want to summarize all of the equations that we've looked at. So first of all, we derived the general conservation of mass, and this is just the really general conservation equation. And so this was d dt. We're going to integrate over the control volume, rho dv, dv plus, and then we're going to integrate over the control surface, rho, the dot product of the velocity vector and the unit normal vector, dA, is equal to 0. So this is the general conservation of mass. And then from that, using Gauss's theorem, we derived we just rewrote this as what's normally written as the continuity equation. So the partial of rho time plus, and then the divergence of rho v is equal to 0. So this is the continuity equation. So for this class and for practical problems where you're not going to be using a computer to solve your problems, you're going to need to make assumptions in order to solve these equations. So the few assumptions we've already made are, first of all, for the case of steady flow. So for steady flow, this d dt term is 0 because there's no accumulation of mass in your control volume. So basically we have that the mass flow in is equal to the mass flow out. And this is because there's no accumulation in your control volume, and so the change in mass with time is equal to 0. And then we can write this with multiple inlets or outlets. So if we have multiple inlets and outlets, we would just sum over all of the inlets and outlets. So the sum of all of the inlets in is equal to the sum of all of the inlets out. And then we wrote the case, so this is just for steady flow. Then we wrote an equation assuming that it was just a single stream steady flow. Well, and that's basically just this. So this one is the single stream steady flow. So this is SSSF. And then we made one more assumption we assumed that we had incompressible flow. So for incompressible flow, the density is constant. So rho 1, I'm gonna rewrite this as rho in is equal to rho out, so the density is constant. So then we ended up with the volumetric flow rate in is equal to, and so the volumetric flow rate in is equal to the volumetric flow rate out. And this could also be summed. So this could also be for multiple inlets and outlets. So V out. And then remember that, just for some more general equations, remember that the mass flow rate was equal to rho 1, and then this is the velocity A. Well, I don't know why I put ones on there, but m dot is equal to rho velocity A, area. And so for all of these, like with this one, we can write this as, so in, this would be rho in A is equal to, and these are all in, is equal to, and then this is out, so rho velocity out, area, and same thing down here, so where we just have the volumetric flow rate, so if the density is constant, this is just going to be velocity times area in is equal to velocity times area out. And this also, remember that the density is equal to 1 over the specific volume, so we can write this as the velocity multiplied by A over the specific volume. So remember, this is the specific volume, this is the velocity. So now it might be a little more clear why we might need to do a mass balance to solve first law equations. So we can get things from the mass balance, like let's say that we know some information for our flow in and some information for our flow out. We can get things that we don't know. So for instance, we could calculate, say, the specific volume of either the mass flow in or mass flow out, or we could calculate the area of one of our inlets or outlets, or we could calculate the density. So we can get a lot of information from doing a mass balance, and we might need some of that information for the energy balance when we apply the first law to open system problems. So I hope this video was helpful. I recommend going through and writing down the derivation yourself. I think that really helps to really understand what's going on with the derivation.